so this is our Honors Chemistry, Section 8.4 lesson video, Part 2 of 5. So let's go ahead and knock this one out, because I'm not going to lie, I'm kind of tired of making lesson videos about Chapter 8. But it's okay, we'll finish at some point. Alright, so in each case, so we finished in Part 1 talking about bond polarity and dipole moments and whether something's polar, nonpolar, or ionic, so we're going to continue that for right now. So in each case, which bond is more polar indicate in each case which atom has the partial negative charge. So again, just like in Part 1, you're going to want an electronegativity chart. So the basis of how polar a bond is it's based on the difference in the electronegativity. So the greater the difference in the electronegativity, the greater the bond polarity. So I need to look at my electronegativities. So B is 2.04, Cl is 3.16, C is 2.55, and Cl is 3.16. Okay, and so again, I'm pulling those from an electronegativity chart. So it says which bond is more polar? Well, the difference between these two numbers is going to be greater. So I can see that BCl is going to be more polar. Then it says indicate in each case which atom has the partial negative charge. Well, since I can see that Cl has the higher electronegativity, that would be partially negative and B would be partially positive. So Cl would have the partial negative charge. Alright, and so we just do the same thing for Part B down here. So the electronegativity for P is 2.19, F is 3.98, P again is 2.19, and Cl is 3.16. So the greater difference is going to be between P and F. So that bond would have the greater difference, and then of course which one has the partial negative charge? Well, since F has the greater electronegativity, it would be the partially negative atom. Alright, so hopefully that one's not too bad. So let's let you try one. So remember, the difference in bond polarity, the larger the electronegativity difference, the more polar the bond. Alright, so it says which of the following bonds is the most polar? So we have S and Cl. So S is 2.58, Cl is 3.16, S is 2.58, Br is 2.96, Se is 2.55, and Cl is 3.16, and Se again is 2.55, and Br is 2.96. Now, for some of you, if you're having to look at all of these numbers and getting a little confused by all of them, you can actually just go through and subtract each one. Like if you're having trouble just looking at it, telling which one has the greater difference, you could go through and subtract all of them. But if you look between S and Se, Se has the lower electronegativity between S and Se. And then between Cl and Br, Cl has the higher electronegativity. So I can tell just by looking at it, it's SeCl. However, if you can't, like I said, you could go through and subtract each set of numbers, and then that would tell you, because you could just look at which one has the greater difference. Either one works, it's just if you can look at it without having to subtract all of them, it saves you a little bit of time. Alright, so let's talk about bond polarity. So if you haven't watched the Section 8.3 lesson videos about Vesper shapes, you definitely need to watch that before you watch this part. So for a molecule that consists of more than two atoms, the dipole moment depends on both the polarities of the individual bonds and the geometry of the molecules. Bond dipoles and dipole moments are vector quantities, which means they have a magnitude and direction. So if they're pointing in opposite directions, they will cancel out. So see, like we already did water in the previous video. We have bond dipoles both pointing towards oxygen, so the overall molecular dipole would point up towards oxygen. Here, C and H are practically nonpolar anyway because their electronegativities are so close, and so in this case it would point towards fluorine because fluorine is the most electronegative. Here they would point towards the oxygens, but since CO2 is linear, they actually cancel out. So even though each bond is polar, the overall molecule is nonpolar because the dipoles cancel. So let's look at some examples of this after we talk about it a little more. So the overall dipole moment is the vector sum of its bond dipoles. if the dipoles are of equal magnitude but in opposite directions, then they cancel out, making the molecule nonpolar. Now that is an important thing to add. These are in opposite directions, but they're also of equal magnitude. So see, this is a CO bond, this is a CO bond. If one of the bonds had been CF, then that's a different magnitude of a dipole moment, and so the whole dipole moment would not cancel out at that point. So if the bond dipoles do not cancel out, then the molecule is polar. Be sure to consider the shape. Okay, so like I said before in the previous video, if you assumed water was linear, then your dipoles for water would cancel. So it's obvious to tell sometimes when they cancel. So like here, if they're all pointing outward, they cancel. It's a little harder with some of the tetrahedral molecules. Okay, so if you have a tetrahedral molecule, if they're all pointing either outward or towards the center, then those still cancel. They're all pointing in opposite directions. Whereas like here, see how they're all pointing towards in, so they would not cancel. So you got to be careful of shape. So let's look at some examples together. Let me make sure I know where we're stopping. Okay. Always got to figure that out. All right, so let's add up our valence first. So Br is 7, Cl is 7, which is a total of 14. If you're not good at drawing Lewis dot structure, go back to 8.2 because I'm going to go fast. All right, so I single bond everybody and make everybody stable. Obviously, since there are just two atoms, linear is my only option. So if I look, my Br is 2.96, my Cl is 3.16, so my dipole would point this direction. Since there's no other dipole to cancel it out, this would end up being polar. So in other words, if your dipoles cancel, it will be nonpolar. If they don't, it will be polar. All right, so next, and it might not be very polar. Like if you look, when we subtract these, it's going to be a very tiny number. But it's still just a little bit polar. So next is SO2. So we add up our valence. S is 6, O is 6 times 2, which is 18 valence electrons. So I'm going to bond everybody, make everybody stable. Then count my electrons. I'm allowed 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That means I have 2 extra. I need an extra bond. I'm going to readjust for my extra bond. So I readjust my octet. And so if I look, I have 3 domains. So this is not a linear molecule. Okay, it's actually going to look like this right here. It's actually also going to have resonance because I could put my double bond on the other side. I know some of you are sitting there like, oh my gosh, resonance is coming back. Oh yeah, resonance never went away. All right, so here's what our molecule actually looks like with its shape. So if I look at my electronegativity chart, S has a value of 2.58. My O's have a value of 3.44. So what that means is my dipoles are going to point down towards the O's. So that'll happen in all my bonds. So because they don't cancel, like they're both pointing downwards, this would be polar. Okay, so that's to see if you thought it was linear, you would think that they're going to cancel out. So you've got to realize it's not linear, it's actually bent, because that lone pair is going to take up space. All right, so let's look at our next one, SF6. So S has 6 valence electrons, F has 7 times 6, so that's 42 plus 6, which is 48. My gosh, got a lot of electrons happening down here. All right, so I'm going to bond everybody, S in the middle, put all my F's around it, make everybody stable, and yes, if you're in my class, I expect to see dots on all of those F's. If you're in somebody else's class, maybe they don't have that expectation, but I mean, it's technically not right if you don't have it. All right, so this has 6 domains, so it's going to be octahedral, so I can just kind of change my 2 bonds to poke out and change these 2 bonds to go back into the board. So if you look at your electronegativity chart, S has a value of 2.58. I'm going to write that real small right there. All my F's have a value of 3.98. So what that means is all of my dipole moments are pointing outward towards the F's. So if you look, because they're all pointing in opposite directions, they're all going to cancel, and this will be nonpolar. Alright, so hopefully this isn't too tricky. Mainly, the thing that you have trouble with is actually doing the shapes from section 8.3. It has nothing to do with whether or not the dipoles cancel. It's over drawing the shapes. So make sure you know 8.3. Alright, so maybe pause the video and try these two. So you're just going to draw it, look at the shape, and determine is it polar or non-polar. Alright, so I'll assume you've done that. Let's look at it together. So N has 5 valence. F has 7 times 3, so 21 plus 5 is 26 valence electrons. So I'm going to bond everybody, make everybody stable. And see, once you get good at Lewis dot structure, you'll be able to go way faster than I was showing you in the 8.2 video. Alright, I'm allowed 26, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So this is my structure. However, this is not the shape. I have 4 domains, which means I'm going to have a tetrahedral-like shape. So it's going to end up looking like this. Alright, so we have our tripod coming down, and we have our lone pair at the top. So if you look at your electronegativities chart, N is 3.04, F is 3.98. So they're all going to point towards the F's. Now technically they all are pointing in opposite directions, but we don't have an up. See how there's no dipole pointing up because of the lone pair? So in general, they're all pointing downward. So this would be polar. Okay, we would have to have one pointing up in order for them all to cancel. Alright, so hopefully you got that one right. So let's look at BCl3. If you've done this one, keep in mind B is an exception to the octet rule, as in it tends to have less than an octet. Remember, Be tends to surround itself with 4 electrons. B tends to surround itself with 6 electrons. Alright, so I'm going to go into this knowing that B tends to only have 6 electrons around it. So if you look, B has 3, Cl has 7 times 3, so 21 plus 3 is 24 valence electrons. So I'm going to start like this, make everybody stable, but I'm not going to make B all the way stable because I already know that B tends to only have 6 electrons around it. It tends to have less than an octet. I'm allowed 24, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So you'll totally miss this one if you don't remember that about B and BE. However, this is not the shape. I have 3 domains. So it's actually going to be more like this because they're all going to be 120 degrees apart from each other. Alright, so next let's see if our dipoles cancel. So B has an electronegativity of 2.04 and Cl is 3.16. So my dipoles are going to point outward towards the Cl's. And so if you look, they're all pointing in opposite directions, so this one would be nonpolar. So even though they have similar formulas, NF3, BCl3, they have different geometries, which makes one end up being polar because of that lone pair and the other one not. So Vesper theory shapes are very, very, very important for determining something like polarity of a molecule. Alright, so moving on, let's start talking a little bit about intermolecular forces. So there's a difference in an intramolecular force and an intermolecular force. Intramolecular forces are the forces within one molecule. So in other words, the bonds. So like in this NH3, these bonds are the intramolecular forces. Intermolecular forces are attractive forces that exist between multiple molecules. So the fact that these NH3 molecules are kind of attracted to one another, they're attracted by intermolecular forces. So think of it kind of as 2 magnets attracting one another. So the first type we're going to talk about is London dispersion. London dispersion forces are the weakest of the intermolecular forces that exist between all molecules. These are the only forces in nonpolar molecules. Okay, so all molecules experience them. But for nonpolar molecules, this is the only type they experience because we're going to talk about different types. Okay, so our first one is London dispersion. And so all molecules have them, but nonpolar, that's the only one they experience. London dispersion forces tend to increase in strength with molecular weight. So as molar mass increases, your London dispersion forces increase. These forces also increase as the chain length of a molecule increases. So see how this is a longer molecule than this one? So these have more intermolecular forces. So it increases as molar mass increases and as the length of a molecule increases. So the next type is dipole-dipole forces. Dipole-dipole attractions exist between polar molecules. And then there's also something called ion-dipole forces. They exist between an ion and a polar molecule. The magnitude of attraction increases either as the charge of the ion increases or the magnitude of the dipole increases. Okay, so this is what a dipole-dipole attraction looks like. We have a partial negative side attracting to a partial positive side, just like a magnet. This is what ion-dipole looks like. These are water molecules. Water molecules have a dipole moment, and it's being attracted to an actual ion. So that's what ion-dipole looks like. And so then the next one is hydrogen bonding. So hydrogen bonding is a special type of intermolecular attraction, not a bond, between the hydrogen atom in a polar bond and a non-bonding electron pair of a nearby small electronegative atom, which the choices are NO or F, in another molecule. Okay, so in other words, you have an H that's partially positive but attached to a highly electronegative element being attracted to a highly electronegative element. So you're looking for N, O, and F in those examples. Okay, it can't just be any electronegative element. So you have hydrogen being attracted to N, O, or F. But the hydrogen itself also has to be attached to a very electronegative element. And then it's attracted to an electronegative element in the other molecule. So London dispersion are the weakest, dipole-dipole tend to be stronger, and then hydrogen bonding tends to be the strongest, because hydrogen bonding is just a very strong version of dipole-dipole. Intermolecular forces of different substances vary over a wide range, but are generally weaker than an actual bond. So real covalent and ionic bonds, they tend to be stronger than intermolecular forces. When comparing the strengths of intermolecular forces in two substances, consider the following generalizations. For molecules with similar molecular weights and shapes, dispersion forces are equal unless there is a difference in polarity. And then for molecules of different molecular weights, the substance with more mass has the stronger attractions. So your intermolecular forces are based on mass, so the more massive molecules have more intermolecular forces, or they're based on the polarity difference, so the difference in the electronegativities. All right, so let's look at a couple of examples and then we'll be done with this part 2 of the video. All right, so it says determine the intermolecular forces that exist in the following molecules. So if you look, it's based on nonpolar and polar, so you need to think back to how do we know if something's nonpolar, polar, or ionic? Well, if something is nonpolar, it has an electronegativity difference of less than 0.5. If something is polar, it's 0.5 to 2, and if something is ionic, it is greater than 2. So that's how I can tell whether something is nonpolar or polar. However, keep in mind when it's a molecule, sometimes it might subtract as polar, but the geometry of the molecule might turn it into nonpolar. All right, so first we have SO2. So remember, the numbers that I'm pulling right now are from my electronegativity chart. So O is 3.44 and S is 2.58. So once I subtract that, I get 0.86. Now we just drew SO2 just a few minutes ago, and so remember it was bent, so those dipoles are not going to cancel out. It is going to be polar, which means it is going to experience dipole-dipole attractions. However, every molecule experiences London dispersion. Okay, so I'm going to circle dipole-dipole because that would be the stronger of the two, though. Okay, so the one that would make the most difference is the dipole-dipole. But every molecule has London dispersion forces. All right, so Next we have CH4. So C is 2.55 and H is 2.1. So when I subtract, I get 0.45. Now, technically that's still slightly polar, but because it's such a small difference, we normally consider it nonpolar. But even if you didn't, when you draw CH4, it's tetrahedral. So all your dipoles would cancel out either way. So since it is nonpolar, it only experiences London dispersion forces. Alright, so let's look at our last one. We have H and F. Now before you subtract, always consider, is it hydrogen bonding or not? So remember, hydrogen bonding occurs when hydrogen attracts to either NO or F on another molecule when it's attached to NO or F itself. Okay, so I have hydrogen, I have fluorine, so this one is going to experience hydrogen bonding. However, remember our intermolecular forces are additives. Technically, hydrogen bonding is a strong form of dipole-dipole, and then all molecules experience London dispersion. I'm just going to circle the hydrogen bonding though, because out of the three, that would be the most important one to know about that molecule. Alright, so I'm going to erase, and I'm going to give you a few to try. And then we'll look at them together. So try these real quick, then we'll look at them together. Let me make sure this is where I intended to stop. Okay, and it was. Alright, so I'll assume you've tried these at this point, so let's look at them together. Alright, so we have NH3. So, I'm going to start by subtracting, I'm not going to subtract my electronegativities because I'm going to look and see if it's hydrogen bonding. So N is one of the electronegative elements that H can be attached to for hydrogen bonding. So I can already tell just based on my elements, this one has hydrogen bonding. However, remember, they're additive, so technically it has dipole-dipole, and all molecules have London dispersion. Now some people, they're not big on whether or not you include the dipole-dipole because hydrogen bonding is an incredibly strong form of dipole-dipole, but I just like to put all of them just in case, okay, just to show that they are additive. Alright, our next one is O2. Alright, so we can clearly tell that one's not hydrogen bonding, it doesn't even have hydrogen in it. So I need to tell, is it polar or nonpolar? Well, it's O bonded to itself. So obviously that will mean it's nonpolar because O is going to be just as strong as O. So since it's nonpolar, it would only experience London dispersion. So hopefully you got that right. Alright, last one is PCl3. So I know it's not hydrogen bonding, there's no hydrogen, so now I need to determine is it polar or nonpolar. So my number for Cl is 3.16. My number for P is 2.19. So I do 3.16 minus 2.19, and I get 0.97. So that implies it is polar, but I do need to see if my bonds cancel out, like my dipoles cancel out, so I do need to draw it. Alright, so P has 5 valence electrons, chlorine has 7 times 3, which is 21 plus 5, which is 26 valence electrons. So I'm going to bond everybody, make everybody stable, and then check my total. I'm allowed 26, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Alright, so this is going to be a trigonal pyramidal molecule, so it's going to look like this. Then I'm going to have one coming out, and one going back. Alright, so P has an electronegativity of 2.19, and Cl has 3.16. So in other words, all my dipoles are going to point towards Cl. Now because there's no dipole pointing up, they will all point down, so they are not going to cancel. So this is a polar molecule, so that means it is going to experience dipole-dipole. So remember, you got to make sure you get all the way to the actual answer they're looking for. Sometimes y'all tend to stop in the middle of it. Alright, but that's the most important ones, but all molecules experience London dispersion, so don't forget that they are additive. Alright, so hopefully you can now see why these sections are so incredibly long, because we keep going back to a lot of other material from the previous section. Alright, so for this one, the main thing is to remember that when you're talking about polarity of a whole molecule, you have to take into account the 3D Vesper shape.